David. So first, I would like to thank the organizer for giving me the opportunity to share with you some flavor of what we are doing right now with lattice Boltzmann methods. So I will mainly focus on some applications that are not related to Airbus, Renault, and Safran engineering programs, but to new problems that we are addressing based on the same issues, on the same numerical methods. First, what I would like to show you today is mainly related to prediction of air quality in realistic configurations. And first of all, of course, in order to do that, you have to have, let's say, a realistic description of the air dynamics and atmosphere dynamics, meaning that this is computational dynamics, but with some specific features. And just to mention them, what we would like to predict at the very end are density of the fluid, velocity of the flow, temperature, but also things related to humidity, because in our applications, the one I'm going to discuss today, humidity of air is of primary importance for some specific applications. So you have to deal with water vapor mass fraction, liquid water mass fraction, and also pollutant, because what we would like is to be able to predict pollutant physics and pollutant dispersion in complex turbulent flows. And to do that, you have to account for many physical mechanisms. The first one, for example, is gravity, leading to stratification of the flow, either stabilizing or destabilizing effects. Flotation, if you are looking at large scales of the flow, coupling with mesoscale of atmospheric flows coming from dedicated software for that. Exactly what we have seen today before. Unsteady, of course, construction of turbulence at the boundary of your domain when you need that. You have to account for phase change if you look at water, evaporation, and condensation. And of course, if you're dealing with urban areas physics, you have to account for the effect of vegetal areas, vegetal volumes, cloud physics, and for all these things, you have to develop turbulent submodels. So just to tell you that, of course, you keep in mind that we have to solve the basic equation of fluid dynamics with a large number of physical submodels coupled to that. And that can be an issue if you look, for example, at optimal programming of all these things on GPU or some devoted architecture, because if you optimize your code at a given time, refining after that the physical model may induce a large amount of reworking, re-engineering of your software. So just to illustrate what we are doing right now, looking at fluid dynamics, we have to solve the mass and momentum conservation equation, which is pretty classical, plus an energy equation. Here what I have put is a temperature equation, plus two prognostic equation for humidity that can be liquid vapor, water vapor, or liquid water. And of course, to close that from a thermodynamical point of view, you have to use the equation of state, and here this is the equation of state for humid air. In terms of numerical methods, because we all know that the numerical method that you use is of primary importance if you look at, let's say, efficiency for HPC after that on massively parallel simulation. The two first equations, namely mass conservation and momentum equation, are solved using a lattice Boltzmann method, meaning that we are not solving the classical Navier-Stokes equation, where we're using an explicit method to solve the Boltzmann equation on a Cartesian grid. On these two key features, this is an explicit method for the Boltzmann equation, because if you remember, Boltzmann equation is linear if you look at the advection, and is nonlinear if you look at the collision. But the collision term is purely local, meaning that when you compute the collision term, you don't have to exchange any data with neighboring cells, minimizing this way the transfer part of your massively parallel computing. And after that, because we would like also to minimize the memory required to solve the problem, you have to find some kind of trade-off between, let's say, efficiency in terms of pure CPU and memory. And for example, for this scalar equation, energy and humidity, and more than that, let's say, pollutant concentration, we decided to use a classical finite difference approach, meaning that we are not defining a set of microscopic distribution function for each scalar, because it would have led to a large increase in the memory requirement. So for the part of the algorithm which is of key importance for us in terms of mass conservation and momentum, we use LBM, and for the rest, this is a classical finite difference implementation. Still focusing on efficiency, what we have done is to use a purely explicit scheme for all the equations, with also the minimum stencil, meaning that in all cases, all the schemes that we use just need the first neighbors to compute all what you need to compute. It can be a gradient, it can be advection. In all cases, we just look at the first neighbors. So now in terms of general organization of the code, they said this is a pretty classical one, meaning that first, for engineering purposes, you need usually to define, to describe a complex geometrical configuration. First, you have a TAD problem. From that, you have to define the surface mesh. And you have some well-known software, Unsteady and Salome, for example. And after that, you have to design a volumic mesh, and of course, to prescribe all the parameters you need. And for that, of course, for practical complex things, you need a graphical interface user unit. Then you have the solver itself, and after that, post-processing, and we know that all these steps are not trivial at all. Basically, all what we are doing is based on C++ programming. This is MPI parallel implementation. And for the CFD part of what I'm going to show, this is based on subdomain decomposition. Typical runs we are doing use from, let's say, 1,000 to tens of thousands cores. And for multi-physics coupling, based on code coupling, for example, when we couple our CFD software to heat transfer software or to solid mechanics software, it is based on MPCCI or PALM, depending on the software and the people we are working with. Another point is that we are more and more asked to have a look at uncertainty quantification and propagation for engineering problems, meaning that being able to run one very beautiful simulation using a huge number of cores is not enough. What we are asked for is to build response surfaces, and to do that, even using optimized response surface building methods, you need to solve your problem from tens to hundreds and even thousands of times, meaning that you need to run a huge number of CFD runs in order to answer the question you are asked. On here, this is another way for us to address massively parallel computing on HPC, is to be able to run at the same time a huge number of simulation in a dynamic way. Because when you build a response surface with, let's say, advanced methods, your uncertainty quantification response surface building algorithm is going to call your CFD software as a black box, and is going to do that dynamically in order to optimize the accuracy of your response surface. Okay, of course, I have no time to discuss all these things. So what I would like to do after that is to say a few words about let's say the organization of the CFD software itself. A key point is that everything is done on parallel, meaning that everything is distributed on the cores that you have access to from the very beginning, meaning that we have several steps. Each steps correspond to a devoted part of the solver. Once you have defined your problem, meaning the total geometry, the computational domain on the geometry of subdomains, but the mesh is not there yet. You have a first step, which is a cutter that is going to, let's say, generate the octree-based data structure and optimize the load balancing between all the cores. After that, you go to the mesher. On each, at this step, all future subdomains have been already distributed among the cores, and then the mesher is going to build the mesh on the data structure on each core for on the domain, on the subdomain that are associated to that course or set of cores. And then the piecer, which is going to refine the subdivision and to optimize the load balancing before the computation. Then you have the scheduler. On that part is going to schedule all the operations. Operations mean that, for example, in CFD, you have to solve your equation in the core of the fluid domain, but you also have to account, for example, for boundary condition. And you can have several boundary conditions at the same point. If you look at corners or edges between two subdomains, on here, there is a part that is optimizing and automatically organizing the different operations in order to be sure that all nodes at the very end will get the good, let's say, scheme and data to be solved. And after that, you solve your problem. We are only addressing unsteady problems, meaning that we have a loop over time steps. And once you have finished with that, of course, you go to post-processing on results. So to illustrate that, if you look at what is done, this is a typical car, full car configuration simulation that we are doing with Renault. When you want to compute the driver of a full car, first defining the geometry of the car. Typically, people use a few hundreds of surface elements. From that, we're going to design the surface mesh. And here, from a few hundreds, you go to a few millions of surface elements. From that, you are going, after that, the software is going to build automatically the volumic mesh with a few millions to hundreds of millions of cells. And what is nice is that it is done automatically very quickly, because from the CAD, meaning that from the geometry to the final volumic mesh, you need something like 2 hours. And after that, of course, you have to simulate the physics in an unsteady way. And because this is a fully explicit method, we have very small time steps in terms of physical time. For 1 second of physical time, typically you have 300,000 to, let's say, 1 million time steps, meaning that our time steps are very, very small, typically 1 microsecond, something like that, or a few microseconds. Okay, now just some examples, a few applications. I'm going to discuss air quality on transport of pollutants in realistic configurations. The first type of applications we're running are related to, let's say, outdoor air quality. And typically here you can see this corresponds to 1 kilometer square of the Shinjuku area in Tokyo, with geometry with details down to tens of centimeters at full scales. And with that, of course, here we are, for example, looking at release of a pollutant at the ground, looking at, on the left, a heavy gas. On here you have stable stratification effect, a neutral gas, meaning that the density of the pollutant is the same as the density of air. On light gas, like, for example, helium, in which you have unstable stratification. On the top, you see unsteady instantaneous simulation. On the bottom, you can see the time average of the concentration over 1 hour. One, let's say, more, quantitative results. It has been done for the Ministry of Defense. And it was a test case defined by the European Defense Agency. The idea is to study the release of, let's say, nasty pollutant in the air in a urban area. And here you can recognize the Champs-Élysées area in Paris. And this is a wind tunnel model used for that. And this is a geometry of the computational setup that we use to recover experimental data. One important thing, and this is why to be efficient in terms of parallel computing is important for us, that because we have very small time step, we need to run the simulation over a huge amount of time steps to have physical times that are, let's say, reliable, meaning that we can do some post-processing that can be compared efficiently with experimental data. For example, here in the wind tunnel, they did some time averaging over 3 minutes, while here we were able to run the simulation over 30 seconds. You can see that there is a factor of about 10, not exactly 10, but about 10, between the physical time in wind tunnels and the physical time we can afford in numerical simulations. And after that, of course, if you look at a quantitative comparison, or if you look at, for example, at the concentration near the ground along the Champs-Élysées Avenue, here on the bottom, you can see that symbols correspond to experimental data. This is the mean value of concentration with an error bar, because measures are not exact, of course. And you can see different lines, both dashed and solid line. Solid line correspond to time average over 5 seconds time of simulated data. And dashed line correspond to the variation. So the RMS value you can get by changing the cycle of 5 seconds in the simulation. On the right bottom, you have the same thing for a heavy gas, which is CO2. And you can see that looking at a neutral gas and a dense gas, you have different physics. You have larger concentration is grown for a dense gas, and simulation are able to recover that with an accuracy that is within the numerical uncertainty, excuse me, experimental uncertainty. Okay, this is the same kind of plot, but for vertical distribution of the pollutant, we have the same accuracy, meaning that in all cases, now it's possible to run simulations that are within the experimental, let's say, uncertainty. Now, something which is a little bit more complex. This is exactly what we're working in right now. We would like to deal with evacuation problem, in which now we have human beings moving in a realistic configuration, trying to escape because, of course, there is a fire, there is smoke, and there is something nasty that we would like to escape. And here, of course, because we are dealing with human beings, you have to predict, in some sense, the way that human beings are going to behave, on the way that they are going to move. And this is why you have to develop a kind of numerical twin for human agents. And this is what we have done, working with people from the social science department. You have a physical model, of course, for human agent, because when you move, of course, you are moving the air around you. So you have aerodynamics, you release heat, because we also release humidity because we are breathing. And all these things are taken into account in the simulation. So you first have to find a physical model for a human being. But of course, now you have to add something else, because we would like to study or to predict the way that people are going to behave. On here, we have a two-level modeling. We have a behavior model, a low-level behavior model, which is going to predict in which direction people are going to move instantaneously, at what speeds, and in different, let's say, psychological states, meaning normal modes, you can just walk like that, or to be in panic mode, and here you're going to rush towards the exit. And this is done using a social force model, which is it's a mechanical model developed by Dirk Hilding 30 years ago, something like that. But you have also to use a higher level behavior model that is going to tell you toward which exits a person is going to move. On here, you have to have a model for decision that is going to use also the knowledge about the environment that people have or not. Once you have your human twin model, you have to couple that with a CFD because it's going to predict trajectories on wakes of the people. So it's going to be used in the CFD solver as a source for momentum, but also for humidity, for heat. And you have your velocity, your flow velocity, so you can compute the pollutant dispersion, including transport by fluid velocity, diffusion, turbulence, gravity effect, if any, on aerosol microphysics. And then once you have the instantaneous concentration of pollutant, you can go back to your human twin model because you have got the instantaneous pollutant dose ingested by each person. And that can change, for example, the behavior of the people. You get also access to the cumulative pollutant dose ingested by each person, so you can go to the health diagnostic for each person. I can see that time is running. I'm going to hurry up. So just to give you the key element of the human twin people, the human twin model. First, it's not possible when you run, for example, a simulation for a concert hall with thousands of people inside to have an exact description of the geometry or the geometry of each person. So you have to find a trade-off, and this is done using the actuator line model in which we are going to recover the good drag, meaning that the force exerted by each people on the fluid will be accurately predicted, but of course we're going to lose some geometrical details. And for example, it was, you can see on the bottom of the slide, this is the difference between a real human geometry on the cylinder. This is what we use, cylinder-like small volumes. You can see that you can get a reasonable approximation of the wake of a human being using a cylinder if you tune in a ad hoc way the forces exerted by the cylinder on the fluid. Okay, these are details. A few words about maybe the social force model. So this is a mechanical model, meaning that here, for each person, you have the mass of the person, you have the velocity of the person. If you remember your old courses in Newtonian mechanics, this is the second law of Newton, okay? Meaning that the velocity, so the acceleration of someone is made of different forces. The first one is the relaxation towards the desired velocity. So we have a targeted velocity associated to your behavioral model. Then you have to account for forces due to interaction between human agents. For example, you don't want to collide with other people, so you're going to try to avoid them. You would like maybe to stay near your family. So this is an attractive forces in that case. On here, you can see that there is, of course, there is here a theta parameter, which is the angle of vision, because you are mostly sensitive to things that you see. And depending, for example, on your status, in normal mode or in panic mode, the angle of vision will not be the same. You can also, if people happen to collide, you have to account for this kind of rebound or something like that. And of course, people try to avoid to collide with walls, so you have some specific forces for solid obstacles. When you do all these things, for example, this is a small meeting room with 10 people. So this is a fluid dynamics mesh. Each cylinder corresponds to one given people with his own psychological model, because you can change parameter for different persons. And after that, if you look at instantaneous view, for example, of the meeting room, this is instantaneous velocity. So you have air flowing from the bottom, because you are here, you have air vents that is injecting hot air, because this is a winter simulation. So here, this is the instantaneous temperature on the right, and this is the instantaneous concentration of pollutants here on the bottom. And now, if you look at the trajectories, this is a 5% cases. You can see here the initial position of all people. On here, in red, you can see the door. And this is the trajectory of all people. Okay. And on the bottom left, this is the instantaneous concentration of pollutants seen by each person during his displacement. You can see that one of them, for example, the person number 5, so this one here, is ingesting the maximum amount of pollutant. On here, on the right bottom, you can see the cumulated dose of pollutant ingested by each person a long time. So you can see that here, the person number 5 is, of course, the most let's say, dangerous one. You can do the same for larger things like a cinema evacuation with 340 people. And this is, for example, these are views of the pollutant concentration at different time after the initial release of pollutant. And here, keep in mind that when people are moving, they're entraining the fluids, so they're promoting the mixing of the pollutants in the air. So this is a two-way coupling things. And after that, of course, if you look at that, this is typically what Ministry of Defense is asking us to do, is to plot for example, the cumulated pollutant dose depending on the initial seat of each person, okay, for pollutant, which is here on the right. And you can rerun the different things, for example, for normal behavior on a panic behavior. So people are not behaving in the same way, they are not escaping at the same velocity, so the mixing is not the same, they do not stay in the room for the same time, so you have different parameters, and you can see that some people will see very different results. On our most complex cases, which is a concert hall with 6,000 people, and this is the same kind of things. Okay, I think that I'm late. Is that right, David?
Yeah, time's going on.
Okay, I just would like to conclude because it was just to show you the results of what you can do in terms of predicting evacuation coupled to realistic CFD software and fluid dynamics with a two-way coupling. Thanks.